Hi everyone. So we're going to cover retrieval augmented generation, in particularly for the healthcare. So as we know, we know about the large language model where we can ask any question and we get the answer, and this answer is a generated answer. So then we know everything about the large language model, that it's based on the supervised learning principle, and the basic mechanism, the fundamental mechanism is predicting the next word in the sequence. And there are different phases where this large language model is trained, which is first is the pre-training phase that creates the foundation model, which is based on the next token prediction. And then we have the supervised fine-tuning stage, which is based on the instruction prompt pair, where we have the instruction, we have the input, and we train based on the output. And then finally, we have the RLHF, which is reinforcement learning from human feedback, which is the alignment stage. So retrieval argument generation is a little bit different from this one. It's an addition on the top of this. So what happens is that in case, because this large language model is trained on certain data set, right? So then its knowledge is limited up to that data set. You can say that with respect to that data set only, the day on which they or on the day when the data set was collected, right? So it may not have access to other information. Okay, and then it's trained on a very general data. Sometimes we want some specific answer to be generated from this data set. So that's where we can pass some information to the question. So we can say the question plus information is passed to this, and then answer is generated based from this information. So this language model can use this information to answer this. Now, what if this information is large? So we have maybe few books, number of pages are there, and we are continuously asking. So every time we need to provide the information. So that can increase the latency. And the cost is also increased if you are using the paid API, where you're passing the information and then you are being charged based on the tokens that has been sent. And sometimes there is a limitation also. And so that's one thing, that the latencies can be increased and the cost can be increased. But on the top of that, even if you are tolerable to latency and the cost, but the accuracy is something that is again a concern, because you're sending the complete information and your question can be answered from a few paragraphs from that information only. So you're passing any irrelevant information to the large language model, and because of that, the accuracy of the answer may be decreased. So that's where the retrieval augmented generation comes to help in all of these three cases. So what happens in retrieval augmented generation is, now the question, we are not passing the complete information, but we are passing some sources of this information, and this information is stored in the knowledge base, and the question or the query goes to this knowledge base, and from this we get some sources. So this may have MySQL, this may have some PDF documents, there may be number of documents or the knowledge is here, and the idea is to get some relevant sources from this and pass this information. So the complete knowledge base has been replaced by sources. Our cost, our latency is improved, our cost is improved, and we are passing the relevant information. That's what it means is retrieval augmented generation. So first you retrieve the relevant information, then augment, question plus augmented resources, this argument, and then the answer is generated by the large language model, right? So that's the very high level overview of RAG. Now, how does the RAG work? So it works similar that we just discussed. Retrieves relevant data from external sources. So we have plugged in external sources, and the first right step is to retrieve the relevant data before generating the answer. And second is argument, which is the incorporating the external knowledge, that may be private documents, PDFs, and databases, into the prompts. So now we added this into the question, and then we get the answer is generated. That helps us to increase the accuracy, source citation, and we can dynamically update. So dynamically update means that this knowledge base is now the external. It's not part of the, we are not sending this to the large language model, but only some information. So this knowledge base is that we have the control, and we can always update that. We can update MySQL, we can update the other private documents or our company policies. Okay, so now we have two things. One is the long context model, and the other is the retrieval augmented generation. Long context model is in the without when we are not using the retrieval augmented generation. So we are just sending the information to the large language model, and then it gives us the answer. So when should we use the long context models? It's usually the smaller data set, no need to use the RAG. You can just pass that one page or a few PDF to that. Complex analysis, like you want to summarize the complete company report, right? So in that case is the complex analysis. We need to see all the documents related to that. Or you can tolerate the delays, like you can send the information, or the low volume, like you have only very few questions to answer, then maybe you can use just the long context model, pass the information and get the answer. When to use RAG? When your data set is large, right? So it's costly, or sometimes it's not, cannot be passed. So then we can use the large language model. Then we want fast responses, especially for customer care. If you want to use that our company answer to the customer should be answered based on our document, then we need fast responses. And for that, we should use the RAG instead of the long context model. Then we are cost effective. We don't want cost unnecessarily to be increased, and we also want transparency. Transparency is important because when we are sending information, the complete information to the large language model, so we don't know whether this answer is generated from this document or the large language model has used their own knowledge. So, but now, in this case, when using the RAG, so it's extracting some sources, and the sources are sent to the large language model. So we can see that whether the answer is correct and what was the context, what was the sources that was sent to the large language model, and then answer is coming from that or not. So we know that where to improve. We should improve it here, or we should improve it here, because that's what it is sent. So if the answer is based on this and the sources are not correct, maybe we need to improve our retrieval process. But if this is the correct, maybe we need to adjust it. So the complete transparency is there over that why this answer is generated. Okay, next. The question, which model will you use? This is just a simple example. Let's say that we have a real-time customer support using dynamic knowledge base. Then we want to develop a chatbot for real-time customer support, and the knowledge base is dynamic. So if the knowledge base is dynamic, which one should we use? Long context model or the retrieval augmented generation? Right. So this question is simple, right? Because it's first it's a real-time customer support. Real time means that we need fast responses, and then it's a dynamic knowledge base. So dynamic knowledge base can be changed very frequently. So in these cases, I think the RAG will be appropriate because we don't want to pass the complete context and that keep on changing. Answer is RAG. Second is, let's say that you want a deep analysis of a single policy document, right? So as you see this question, that it's a deep analysis first, right? So deep analysis means that whatever and it needs to be, the language model needs to read the complete or access the complete policy document, and then it's a single policy document. Then it's maybe one question. It's not very frequent, low volume. So all of these things indicate that we can use the long context model instead of the RAG model. So answer for this one is RAG. Okay, so now if you want to implement the RAG, so you can, there are different frameworks, LangChain, Llama Index, and there are other, maybe other frameworks there, or you can create your own framework. Okay, so the embedding is something very central. So I'm going to demonstrate the RAG pipeline from the scratch, not using any framework, but of course you can improve that with the frameworks, but I'm not going to use any frameworks. It will be from the scratch. And the core thing in that the pipeline is the embedding, right? So let's see just very briefly what is embedding. So for the textual data, the GPT series or Llama can create vector embeddings of words, sentences, paragraphs within their internal layer. So what happens is that you can pass the word, you can pass the sentences, you can pass the paragraphs. So an embedding can be created. Embedding is something, some floating point number. It's a vector of some floating point number. So this vector can be maybe this is just a 10 vectors shown here, but in practical it can be 1500 numbers or 3000 number, depending on how much embedding size you want to take, which model you take. But the idea behind these embeddings is that these embedding represents some semantic information about the text. If these are two similar words, then these embeddings will be similar. If these two sentences, if similar sentences, these sentences will say. If they are opposite, then embeddings will be very opposite. Similarly, for image data also, image also can be converted to the, using convolution neural network, we can convert images to the embeddings. Similarly, for audio data also, that image embedding techniques to visual represent audio frequencies can be converted using spectrogram. So everything can be converted to the embedding, right? So the idea is that we will use embedding to find out the similar information. When the question is asked and we have the knowledge base, then we will convert question to an embedding, and we will have a database, which is the knowledge base. We have PDF document, and we'll convert the PDF paragraphs to different embeddings, and we'll find out which of the embeddings are similar with the question, and that will be our sources. So that's the idea. And now, how do you find out that two embeddings are similar or not? So if the vector, let's go back to the vector. Let's say we have a vector A and we have a vector B. Now, these two vectors are similar if the angle between these two vectors is almost zero. Then we'll say they are overlap, right? So, and similarly, these two vectors are very different and these two vectors are opposite. So the idea is to find out the angle between, so we know the embeddings, we converted this embedding. So next step is that which of the embeddings are similar. So idea is to find out the angle between these two vectors. So that's what thing that we need to find out. Just find out the angle. So one of the method we can use is the cosine similarity. Cosine similarity gives us the angle, and we can take the dot product and divide by the magnitude, and then this gives us the cosine angle, and this angle will be between -1 and 1. So if the angle is 1, right, so if cos 0 is 1, so if we can say if this cos theta is 1, it means that the theta is 0, and 0 means that both vectors are very similar to each other. Or it's not, doesn't have to be exactly 1, but as long as it's close to 1, we can say that this is an angle is close to 0. But when the angle becomes 90, that it becomes cos 90, and we know that's 0, then we can say that these vectors are very different from each other. And here, if this angle is 180 degree, when the cos theta is -1, they are very opposite to each other, right? So we are going to compute the cosine similarity, that's the cosine of the angle. So we are concerned about these values 1, 0 and -1, because these are encoded, these information 1, 0, -1 encodes the angle between these two vectors, whether the vectors are similar or not, right? So essentially we'll say if it is equal to 1 or close to 1, then it's similar, otherwise it's not similar. So the role of embedding in similarity search has been very popular from a few years. Embedding is the key to the similarity search task. Deduplication, like if you want to remove duplicate images, paragraphs, you can convert to embeddings and then find out which of the embeddings are and the angle between those embeddings. If the angle between them these embeddings is 0, or sorry, if the cosine similarity is 1, that means angle is 0. So if the cosine similarity is 1 or close to 1, then those things can be removed, right? And then we have recommendation system also can, or you can use the or using this cosine similarity similarly anomaly detection or reverse image searching. Reverse image searching, that you can convert image to an embedding, and then you can use the match the embedding and then display the images which are close to the input image, right? So all of these things are being embedding can be used. Next step is the vector databases. So now we have seen the embedding, so we can store these embeddings and manage these embeddings into the database, right? So that's the vector database. So keep and manage the embeddings. So vector database, we can have the we can do using vector databases. We can do the semantic search, and these are specialized databases that can store and manage the embedding. So you can write the like we have used the MySQL query. So now you can write the query, and this vector database can give you the semantic similarity, not just the keyword similarity, but the semantic similarity based on the matching embeddings. So that's the key feature. Efficient storage. It can handle large volume of complex data as embedding. Then the vector databases can do the semantic search. It can compare query embedding with the stored embedding and give you the result. And why use vector data? Because it's fast and relevant retrieval of the similar items. And the vector database understand the intent behind the queries, not just keyword, but the intent behind the query. And they can give you the, of course, we can use the keyword search as well as the semantic similarity search. Okay, so now we'll, I think, jump to the RAG pipeline for the healthcare sector, where we'll develop the RAG from the scratch. This was the first attempt, or you can say maybe more, not the first attempt, because there may be some smaller attempts there. Because you can say this was maybe some serious attempt from Medical Palm. This was large language model for Google research, available here. So it's preprint in 2022 and was published in Nature in 23. And this was the first AI to exceed the 60% pass marks on US medical reasoning, medical licensing exam. Right, and after that there have been an updated model as well. Okay, so we're going to do something similar, but not exactly similar, but just to give an idea that how the medical reasoning can take place. So I'm using this dataset, which is available on the Kaggle Macrobat dataset. So this data set is of detailed patient medical reports. So this has reports of the medical patients with a complete history and the annotated information, and information about the patient, their gender, age, and other things. So this data set aims to advance healthcare analytics and improve the patient care and medical research. So that's the idea. So this is how the dataset looks like. So the dataset has number of files for each patient. Patient is encoded, for example, in the number, and it is ANN. ANN is the annotations file, and there is the text file. So the text file describes the case of the this patient. Right. So we are going to build a medical RAG pipeline from the scratch, an application that can sift through patient data and answer questions. So the idea is that we have case history of number of patients. Now the doctor wants to see that what can I use this treatment, or what happens if I use this treatment for this particular patient, and what was the history of that, right? So we want to give the answer using these information. So for this particular, you can say the project, we're not using the annotated information. We're using only the idea is to just explain the RAG pipeline. So we'll use only the text file. But if you use the annotations file, then even you can improve the accuracy much better than that. Okay, so this is a sample text file for this particular patient. So we're not using the annotation. So it says case 28-year history, person had this. So it's complete text is written. You can read it from the file if you want. This is a second text, second file, second patient. So it says a 41-year-old man with weight loss, and this has happened. So this is what is there, right? So we have the like similar history of about 200 patients. We have history as well as the annotations file. So we are going to use this text file. Okay, so now we're going to start the RAG pipeline. So all of these libraries are very simple libraries, and the only library that I've used is OpenAI. So you need to register the OpenAI and get their API key and import the API key and keep this API key into the environment variable. So that's what the assumption is. Right. And then we are also using, because for cosine similarity, we are using the sklearn. Just all our basic Python libraries. Now, the first step, let's see that whether you have installed the OpenAI API key in your environment variable or not. So that's what we're checking. If os.get environment variable, this is the variable that should be set in the environment OpenAI API key. If you don't know, then you can check the OpenAI website and get the key and save this variable accordingly. Okay, so we are assuming that you'll say you'll get API key not found. In fact, you'll get API key retrieved successfully. So once you are there, you can proceed to the next step. Next is the embedding model. So for embedding model, I'm using text embedding 3 large. And there are two models, text embedding 3 small and the large. Small is with the 1500 embedding close to, and the large uses 3000 embedding. So not very costly, but you can use maybe small also. That should be okay. It gives good amount of accuracy, right? So that's the embedding model. Next is, and this is a function that generates embedding. So I have written it like this. So it's a text to embedding. So give the text to this function, and it will model is by default, right? So you can pass if you want to change the model, but you will give the text, and it calls this OpenAI format of getting the embedding, and it returns that embedding. So you just need to give the text, and it will give you the embedding. So we'll keep on using text to embedding function. Next, let's see this now, whether it's working or not. Before we start using the data set, let's see this. So let's say this is the question. What are the symptoms for a patient with repeated hemoptysis, right? So that's the question. And then the answers are let's say that there are two answers. Answer one is, it says cloud computing optimizes data storage and processing, but has no role in treating hemoptysis. And answer two is, there can be thoracic pain that intensify while breathing, as well as a strong dry cough that may persist. So actually, this was answer extracted from this data set. Okay, so let's say that these are the two answers. Now, if you see carefully this answer one and question one, right? So question and the answer one. Question has the hemoptysis, and this answer one has hemoptysis. Treating what is there, right? So there are some keywords matched in the answer one, but there is no matching with the answer two, right? So let's see this now, whether the embedding cosine similarity is working right or not, whether the embedding related to answer one is close to question one, or the answer two embedding is close to the question one, right? So that's the idea. And we're going to find out the cosine similarity between question and answer one, question and answer two, and we'll find out its value, whether this is close to 1 or the question 1 and answer 2 is close to 1. Because if it's close to 1, then it means they are similar, right? Or maybe which is higher, right? So we're not concerned whether it's close to 1. So this may be 43, this may be 53, which is good, or right? So we want this is should similarity between question and answer 2 should be higher than the answer 1. That's what our intention is, even though the keyword is there. So for that, what we do is we'll use this our formula, which is the text to embedding. So we'll pass the question first, and we'll get the question embedding. Then we pass the answer one, we get the answer one embedding. We pass the answer two, and we get the answer two embedding. Now we have three embeddings, and we are going to find out if you see that you want to print the length of these embeddings. So it prints 3072. For large model, it is 3072, and if you use a small model, then it will be 1500. And you can see if you want and the floating point numbers, right? So you can just see, but it's no use of actually looking at those numbers. We want to look at the cosine similarity, right? So let's see this now. Cosine similarity of question embedding and answer one embedding. So we are matching what's the similarity between question and answer one, and what's the similarity between question and answer two. And it says that question and answer 1 are 37% similar, 0.37, and question and answer 2 is 0.43, which is actually a good answer. So it says that answer 2, although the keywords were in the answer 1, not in answer 2, but still the similarity of answer 2 is that's what we want. So it means that we don't have to worry about the embedding. So embedding is working fine. So that's we have tested it with a very small data set, right? Let's go back to the dataset now, right? So we have this Kaggle Macrobat project dataset, and what we are going to first create is the CSV file and the embedding file, right? So CSV file, now as you have seen that there are number of files, right? So each patient has individual file. What we're going to do is we're going to create one CSV file where the history is, everything is there in that CSV file. So we are going to have one row for one patient, second row for second patient, third row for third patient. And then for the embedding file, so we'll use this file, and then we'll call the text to embedding on each row. And then based on that, we'll create an embedding corresponding to that patient. Now, this embedding can be created on the complete row, or this row can be further divided into multiple rows, and then we can basically, you can convert the complete file to an embedding, or you can convert this file to different paragraphs and then convert those paragraphs to the embedding so that you have a better similarity search, right? So that's what we will do that, to convert file first to different paragraphs and then complete the embedding. So that's why we have two files. This CSV file will be a combination of the file. Let's do this. So I have written this function create CSV. So this is the CSV. We'll give that we want this CSV file to be created, right? If it exists, then it just returns. So it already exists. Otherwise, it just search all the txt file, data raw star.txt, and it merge all of these txt file and say that's the file and that's the content, and it returns the data frame. And it saves this data frame and to this file. So it means that the file exists. Okay, so this is what it will be created. So we have file. In the first column, it's file. And then in the second column, we have the content from different file, right? So now if we want to ask a question, so we need to find out in which of these rows the most likely the answer may be. And these are, I think, 200 rows. So we'll see it later. Right. So if I read this file and print, it says 200, so it means that there are 200 rows and two columns. First column is the file and the second column is the content, right? So from it's not possible to that one can read these 200 files and then can get the answers practically. And keyword search, as we have seen, may not work, because that will give you any answer, even though it's talk about the cloud computing and something, but it will just it's not a semantic similarity search. So that's where we're going to work on, that converting this content to an embedding, but not just complete content to an embedding, but first divide this content to a smaller paragraph and then convert to embedding. So that will be our next task, to create the embedding file. So split one row. So I have written another function which is split one row into chunks of 1024 characters. You can choose 1024, 4000 character, or 500 character. It depends. So depends on the data set, depends on the questions to be asked, and other things, right? So let's say that for simplicity, we're using 1000 characters. So here we are saying that split text in chunks. So pass the text. So that's the complete paragraph, and say that I want to convert this to the 1024 characters, and then it returns a list of the chunks. So the complete text is converted to a list with maximum 1024 characters. It can be less if the size is not much in multiples of 1024. Okay, now split all rows. So we know how to, this is a function that splits into chunks. So give the text and it will create a list of this, but we don't want one text, only one row, but we have to implement this on the complete data set, where we pass the complete all the rows. So now it's a create chunk. This another function will pass the data frame, and this data frame uh, goes row by row. It says df content, so one row is selected, and then just new line characters are replaced, and then we call this split into chunks. So we call that function on the content, and then we add this to it. So this also gives a list of the chunks, but now this list of chunks is based on the complete data frame, right? So which is the 200 data set rows. So this 200 rows will be now more than that, because each row will be converted to multiple rows. Let's see now how many rows are there in this. So we say read CSV first, we get the data frame, and then we'll say create chunks of this data frame, and that's the list of the chunks, and this is a list, not the data frame. And if it say what's the length of the chunks, it says 651. So we had 200 rows, and from 200 rows we have converted to 651 rows now. So now each row is being to be converted to an embedding. So for that we'll use the function which is the text to embedding. So now it's the file to embedding. So you give the CSV file, it will read that CSV file, will create to the chunks, and then will generate this embedding file. And this embedding file, as you've seen, we are using it here, the function called text to embedding. Right. So this file will create chunks, and then it will create chunks, and then we read the chunks, read the CSV file, create chunks. So the 651 rows are here, and then for each chunk we are calling this function which is the text to embeddings, and we are adding this embeddings here, right? So this is a list of embeddings now. So now we can create another CSV file which has the content and also the embedding. So this is essentially can be done in the vector database, right? So right now we're using a CSV file, so this part definitely can be replaced, can be done in the vector database. So we're using df updated to CSV, so this embedding file has been created now. And this is how the file will look like if you want to open the file to embedding. So if you see this, this is the chunk, and that's the floating point numbers corresponding to this paragraph, right? So we have created the embeddings. And next step will be, now if we have a question to be asked, so we're going to find out whether this question embedding is similar to this one, this one, this one. These are 651 embeddings, right? So that's our task. So we're going to find out the cosine similarity. But now this is happening at the local system, not on the You're not giving the context to the OpenAI or large language model. So this you can do it on local computer where you have access to these embeddings, and every time you ask a question, you do the similarity search. You convert for question, you need to convert embeddings from the same large language model, but then similarity is something which is in local. So next step is get the context for the query. So context is means that we want to see which of these paragraphs are similar to the question embedding. Okay, so that's the context. So get the relevant indices. So idea is to get the relevant indices first. Which of the rows? So we have 651 rows, and we want to see which of these rows are similar to our question embeddings. Right. So this another function. We have get relevant indices. So that's the data frame, right? So that's the data frame is the embedding. It has the embedding. Then we have the question. So this is the question that we want to ask, and chunks to retrieve. So I want three chunks from this data frame. That what are the chunks that, or maybe what are the rows that may have answer to this question. So that's the idea, and this will return the indices only. Right, so question embedding. So first we need to convert this question to the embeddings first, because we are doing similarity search, not the keyword search. So this question will be converted to an embedding. So we have question embedding, and now we have this one that we are computing the cosine similarity on the question embedding and the complete embedding list. Question embedding and embed list. So we have complete list, and then we have the question embedding. So that will give us the cosine similarity with all the embeddings, right? So the next step will be, so if we have the embeddings from all the lists, right? So next step will be to find out just sort these embeddings and find out the top one. So just argument sort and cosine similarity, reverse this, and then get the top. If it is 3, then starting up to 3, right? So 3 embeddings on the top after reverse sorting. So we get the indices. So this will return a sum embeddings, 3 embeddings. So let's see this. What's the output from the question? Let's say we ask what are the symptoms for a patient, repeated synopsis. So it's a file to embedding. So just get the file first, which is the embedding file. CSV file, embedding file. So we get the data frame and then get relevant and pass this data frame and say this is my question. That's the question we pass, right? So and the default is 3 embeddings. So it will say print indices. So it says that 553, 191, and 588 rows have the paragraphs in these rows are similar to this one, right? So this is the based on the cosine similarity. So we can use this information and pass this to. So that's the retrieval step. So our retrieval step is done, right? So, but this is only the indices, but these indices cannot be passed to the large language model or OpenAI. So what we need is corresponding to these indices, we want the text, but that's very easy because we have the numbers and then we can just get the text corresponding to that. And then the text from this, text from this, text from this can be merged, can get one large text, and that we can pass that this is the question plus the information, and that goes to our next step. Next function is show resource. Let's say that we want to see what's happening here. So that you pass the data frame and pass the indices. So that's all functions written by me. So you just pass the indices and it will find out, say chunk this and will give some space, and this is what it shows. So you say what are the symptoms, so we get embedding, get relevant, and now using show resources. This is the data frame and I want to see these indices. And this is what you will see. Chunk 1, chunk 2, and chunk 3. So this is what the means of the transparency. Now, these are the 3 chunks that cosine similar, based on cosine similarity, the answer lies in here. But if it's not there, then maybe we need to improve on some other similarity mechanism, maybe cosine similar not working, or maybe the context length, which is the 1024 character, is not good. So we can work on this, right? So what's the, or maybe we can add some keyword matching also. We can do both, like the cosine similarity as well as the keyword match. We will find out from the data set. And idea is that this is the context which is going to the large language model. This first should be improved, and answer must lie somewhere in these paragraphs. We don't have to find out the exact answer, but as far as it is in one of the chunks or nearby, we are good to pass to this large language model. Okay. So next is the get context. So get context is just nothing actually, just using the space, merge all the content from the indices, right? So that's the return the context. Right. So we're not passing the chunks in the order, but you can also think of like we can have some improvement here, that we can reorder these chunks based on some other parameter or mechanism, and then we can join this. But we're not, so far it's going to be a very simple pipeline. We have just joined using the space. Okay, next. Let's say this. What are the symptoms for a patient with repeated hemoptysis? So that's the question. We get the embedding, we get the relevant indices, we get the context now. And let's print the context now. So this get context is, it has merged all the indices, text corresponding to these indices. And if we print this, that this is what is returned from the get context, right? So this is will be passed. This is our information or the sources from the knowledge base, and this will be passed to the augmented with the question to the language model. Okay, so now since we are now going back to the language model now, so we need to do some prompting techniques. So our system prompt. You are an assistant and expert in answering questions from a chunk of content. So we're telling that you are an expert assistant, of course, an expert in answering questions from the chunks of content. So we're giving you need to answer based on the chunks that we have passed. If you can't answer from the given chunk, say that you can't answer this question. So this is important. If you really want your answer not to be generated from their own knowledge base, but only if coming should be coming from the chunk. And if it's not there, then it should say I can't answer this question. Okay, now this is the user prompt. So in this user prompt, this is the system prompt which are giving a broad instruction, and in the user prompt we will give the question as well as the answer. So it says that. So the context plus the information. It says read the following information that might contain the context that might contain. So context may be there, context not be there, and you require to answer the question. So you can use the information starting from the start of the context tag and end with the end of the context tag. So we're telling that that's the information start and that's the information end. So you need to use the information available there, and here is the content, start of the content, and then we pass this context, which was the complete paragraph generated by merging all the relevant indices. So that's the context will be replaced, and this is a formatted string, and then the end of the context. Please provide an informative and accurate answer to the following question based on the available context. So we're saying that we're being polite also, no need, but we're being polite here and saying uh, provide an informative and accurate answer using this context based on the question. For this is the question and question. This question will be replaced with the actual question, and then we have the answer colon, and then we have the space, right? So then we are expecting that the language model can fill this now. Using this context, this question can be answered. And now, because language model, we have to generate prompts for each question. So I've written a function for this, which is the get prompt. So in this get prompts, you have already the context and the question. So these are the two things that we need to change every time. Question is the question that every time people will ask different question, and the context will depend on the question, and this context is coming from the relevant indices. So these relevant indexes may be 3, maybe 5, maybe 10, maybe 1, and this context is the we have merged all the relevant indices. So that's the context. So now when you pass question and context, it knows what's the system prompt, it creates the user prompt, and it returns the system prompt and the user prompt. So this is the retrieval process, and it will be augmented using these prompts. So system prompt and user prompt. So these system and prompt, user prompt will go to the OpenAI chat model. So now create messages from the prompt. So this is the format of OpenAI, which is the create messages. This is my function, but what it does is it creates formats of this type which the OpenAI model use. You pass this, we have created system prompt and user prompt, and we pass to this function, and it create a list like this one. It says role, system, content, system prompt, role, user, content, user prompt, right? So this is just a format of OpenAI. So now we have the prompts, and now another function which generates the chat response. So this chat response will pass these prompts to the forum model, and then we'll get the answer, and it will display that answer from the forum. So chat response is system prompt by user prompt, and we are using the GPT-4o mini. Temperature has been set to 0 because we want definite answer. We don't want any hallucination. We don't want any creativity here. We want everything from the data set. Right, and then we have the client, and then create messages. We'll create the messages in that format where we'll pass the system prompt and user prompt, and then we use this completion, which is the client chat completions, create, pass the model, pass the messages that has been created using this format, and pass the temperature value and return the content corresponding to this. So the idea is just to create the prompts, right? So you can create those user prompt and system prompt and give it to the generate chat response, and it will return you the prompt. So the messages will automatically be created because we have written a function for that. Okay, next. Now we're going to use the RAG pipeline. We have already completed the RAG pipeline. So we have question again, what are the symptoms of a patient with repetitive mopsis? So for this question, first, we need to have access the embedding. So we have the data frame. So we have this CSV file and we need embedding file. So we get the data frame corresponding to the embedding file. So this data frame now has the embeddings. Now we're saying this question, pass this question and this DF. So this get relevant indices will convert this question to the question embeddings and will do the cosine similarity and will return us the 3 top embeddings. If we want 5, then we need to write it here. So it will give us the 3 relevant indices. So we got the 3 relevant indices. If you want to see those text correspondences, go ahead and see, call the show resources. But right now we are not interested. And then we are saying get context. So from these indices will be passed to this to get context. So this get context will get the text corresponding to these indices, will merge those indices and will create a one large paragraph, which is the context. And now we have the context, we have the question. So this is the information from the knowledge base. This is our question. And we're going to give this to the get prompt. So we'll pass the question, we pass the context, and it will give us the system prompt and the user prompt, right? So this system prompt and user prompt we are giving to the generate chat response. So this system prompt goes here, user prompt goes here, and this system prompt user prompt are converted to chat messages sent to the OpenAI chat model, and then it returns the answer, and that's the answer, and we return the answer, right? So we have only these 6 steps. Of course, it's a lot behind this, but these are broadly the 6 steps where you have the question, you have the embedding file, get the relevant indices, create the context, create the prompts, and then set these prompts to the model and then get the answer. So let's see this. What's the answer for this one? It says the symptoms for a patient with repeated miosis as indicated to provide the context, including episodes coughing up blood, which can vary in the volume. So it looks like a very perfect answer. Like I don't know whether it's highly perfect or not, but as the question has been asked, it's a highly relevant answer because based on the question, right? So that's the RAG output from the based on our question. Next, let's change this question now. So, is the bleeding possible in case of hemoptysis, right? So that's the different question now. So now, if that the question is changed, so question embedding will be changed, your indices will be changed, your context will be changed, and based on that, the answer should be there, right? So what we've done is the question again, we get the same file, we get the relevant indices now based on this question. So we're passing this question, so these indices will be different, and these indices, your context will be different. So if your context is different, question is different, your prompts will be different, and then you pass these prompts and you get the different answer now, right? And then let's see this answer corresponding to this one. It says yes, bleeding is possible in case of hemoptysis as it is defined as coming. So everything is relevant. Yes, so the answer is very much in sync with the question in both the cases. Now let's see this. I'm asking another question. What is artificial intelligence, right? So this is all healthcare data set, and we know that what is artificial intelligence is not in that data set, and we're just checking whether what is the answer. But the step is same, that we have the question, we get the embedding file, we get the relevant indices now, we get the context, 3 top matching answers, and then it will get the prompts here for these question and the context, and will generate the chat response, and then and it says I can't answer this question. And that's what we expected, that anything outside this domain should not be answered. It should say I can't answer this question. Anything within the domain should be answered, right? So this is what is the retrieval augmented generation. So what is important so far? If you see this, so first prompt engineering is important. If your prompt engineering is not good, then it can even say, it will not say I can't answer, it will give you some answers, right? So your prompt engineering your prompt should be good and to the point, specific. And AI is not like Google or Bing search engine that where you can just give the question and get the indices. So that's the context. So the context is something which is searched by the Google and Bing also, that you get these resources, but they don't know the answer. But artificial intelligence is reading those resources and creating an answer using those resources. That's the next step. So for that, the you should have good the retrieval steps should be good, and then your prompt should be good, and then generation steps should be good. So AI needs more and relevant context to get better answers in the reasoning. So what are the challenges? Challenges are first chunking. So how you are going to chunk the data set, maybe 1000 character, 500, 2000, 4000, depending. So dealing with multimodality, so maybe images are there, maybe other documents are there, or audio file, video files are there, updating documents, how you are going to update these documents, how you are going to maintain the compliance, and how you are going to evaluate the RAG performance, whether this is correct or not. So like, so if you change the chunk, you want to see the performance, like if it's with working good with 2000, working good with 500. So you need to worry about these things. And the compliance here, and no personal information should be sent, no personal information should be retrieved. So you need to see it from this perspective. So small chunks might miss the connection, and maybe more large chunks may have some irrelevant information. Multimodality, text is there, image is there. How do you are going to use in the same latent space? That can be difficult. Implementing dynamic updating mechanism for the vector. So you want to update your model, and then accordingly your embeddings should be changed, or you want to update the embedding model, right? So if you want to change not OpenAI model, maybe let's use the Llama model, or you want to try your own embedding model. So that's another challenge, that you need to update OpenAI is not or the large language model is not concerned about which embedding you use. You may use any embedding, because we are not sending the embedding there, we are sending the text there, and the answer is generated from the text. So embedding is something which is independent of your answer. Compliance is another crucial aspect that we have to take care. An important aspect to consider in some retrieval system is the balance between latency and the quality. So you want fast response, right? And but you want a high quality response as well. So we need to see that how, because if you send more information, like so if you say let's say we pass one only, the quality may reduce, like but the latency will be high. If you say let's pass the top 10 indices, so the latency will be reduced, but the quality may be high. So implementing a combination of different methods such as keyword and embedding retrieval. So you can use the keyword search also. Right now we have used only we have created the context using the embedding only, right? So you can also implement the keyword search and get some context from the keyword, some context from the embedding, and then merge those contexts and send that context to the language model. So that may, but the latency will be high, because as you increase the context length, then the latency is going to be high. The cost of paid API is also going to be high. So retrieval step in RAG system is critical for the overall effectiveness. So this is very critical, that how you're going to retrieve the sources, whether you're using only embedding search, you're using the keyword search augmented with the keyword search, or you are also adding some other searches into that. And you can use the Llama index. That's much better for this one. And that's what I was meaning, that hybrid search. So not only the embedding search, the idea is to use the hybrid search. The embedding search may not always be the most effective method. So you can use the keyword lookup plus the embedding search for the context, and that can be sent to the language model. And we can use the Llama index framework. And next step will be the fine tuning the embedding model, right? So you can also fine tune the embedding model based on that, because embedding model is independent of the answer generation model. So we can fine tune the embedding model, because if embedding model is fine, then you don't need to use some higher end model. You can also work with the lower end model. You can reduce the cost just by fine tuning the embedding model. So this is another option where the people may think. The next will be how to monitor, because you're fine tuning, you are using different context length, chunks, and everything. So number of parameters are there, as you have seen that if we have to deploy this RAG pipeline in for actual use, so there are different parameters. So we need to find out what's the right set of parameter. And for that, we need to evaluate it. So what's the accuracy, semantic similarity, and reliability? So the Llama Index has some libraries that can be used to evaluate the RAG pipeline. So first step is the correctness. First, of course, the answer must be correct. Assesses the alignment with a predefined reference answer. So you should have some referenced answers, and then the generated answer must be something similar to the generated reference answer. But for that, we need some label data to verify it. Then we have the faithfulness. Faithfulness is something that it's not distorting or hallucination is there. So avoid distortion or fabrication of source material. So we want answer to be coming straight from our sources and not maliciously or distorted from that sources. So that's the faithful. So the model is faithful to the sources provided to that it. Next, context relevancy measures the relevance of retrieved context to the query. Context relevancy is that we want to measure whether the context that has been retrieved is relevant to the query or not. You send the query, but the context retrieved is very different from this. Of course, if you're saying the different, then if our prompting technique is good, it can say that I can't answer this question like we have done. So you ask the question of what is artificial intelligence. Of course, we are not checking any threshold on the similarity. We're just saying whichever the top. So there will be some paragraphs always be there, and that will be sent. Of course, then model needs to think that whether there is an answer or not. But in any case, the retrieved context is still very important. So we aim to retrieve and utilize information closely tied to the user's request. So idea is that the context to be retrieved, which is very close to the user's request. And next is the guidance adherence. Is our model uh, is in accordance to some guidance or not, like some style, we want answers to be generated in some particular style, it should be factual, it should be ethical, right, and meet some norms and addresses the query. So that's the idea, that our generated answer. So I also think these can be included in the prompts, prompt using prompt engineering. Then we have embedded semantic similarity, uses similarity scores between embeddings of generated and reference answers. So you can use the similarity embedding, like we are going to evaluate it, right? An answer generated is correct or not. So for that also we use the embedding. So we have generated answer embedding, we have reference answer embedding, and now these embeddings must be similar. So that helps that, yeah, your generated answer is correct. So what are the best practices for building RAG systems? First, incorporate the vector. We have not used in this lecture, but of course, it's highly helpful and encouraged that we should use the vector database that can handle multiple queries in real time. So if you deploying it on for a customer or different physicians, so if you use the vector database, then it will be highly efficient. Then multiple queries from multiple users can be answered in real time, and it can also reduce the latency by quickly retrieving relevant embeddings, and it's ideal for high demand applications like real-time chatbots or dynamic search engines. Then use guardrails for responsible AI. So guardrails is that when the physician or someone asks the question, then first that prompt is classified under whether it should be passed or not, right? That's the first step. And similarly, answer also, we want to check whether the answer should be passed or not. So that's called the content filter. Restrict the model from discussing sensitive topics. Like, so you have created this RAG pipeline for algorithms, but people can ask any question. So first thing is that bring the model or classify the prompts so that no sensitive topic like politics or any bias question is answered by this model. Then language customization, instruct the model to adopt a specific tone or style, formal, conversational, so that can be trained. Then privacy protection measures also sanitize the input, remove any sensitive or personal information. Similarly, retrieve guardrail, ensure only authorized and non-confidential data is retrieved. This is the retrieval guardrails, and then minimize hallucination. Implement mechanisms to verify the accuracy and reliability of responses. Like, so you're sending some information to the language model, and then the idea is that it should not hallucinate, it should not distort the fact, it should not create something which is not correct. That's all. Thank you.